Your FastMCP server has dynamic templates, but how do you actually discover and inspect them programmatically? You'll see how to list all available resource templates with their URIs, names, and metadata, including custom tags, using just a few lines of Async Python. The pattern even handles nested metadata safely, so you won't hit errors if fields are missing.
Async with client. Templates equals await client list resource templates. Hash templates list MCP types, resource template. For template in templates. Printf template URI, template URI template. Printf name, template name. Printf description, template description. Hash access tags and other metadata. If hassetter, template meta and template meta. FastMCP meta equals template meta get FastMCP. Printf tags, FastMCP meta get tags.
This demonstrates the metadata-driven resource discovery pattern, where dynamic capabilities are exposed through structured introspection rather than hard-coded endpoints. The pattern treats resources and templates as first-class entities with self-describing properties, enabling clients to discover and interact with server capabilities without prior knowledge. What makes this distinctive is the separation between capability declaration, metadata, and capability implementation, resource handlers. The approach works by standardizing resource metadata through a consistent schema, allowing clients to query available resources and their properties before making targeted requests. By embedding tags, descriptions, and URI patterns in the metadata, servers provide a discoverable interface that adapts to changing capabilities without versioned API contracts. This creates a loosely coupled system where clients interact with resources declaratively, focusing on what they need rather than how to request it. This pattern solves the problem of rigid API design in dynamic environments, particularly useful in microservices, plugin architectures, or AI tooling where capabilities evolve frequently. It reduces boilerplate by eliminating manual endpoint documentation while enabling richer client interactions through metadata filtering. The trade-off is slightly higher initial complexity in metadata management, but the payoff comes in long-term maintainability and adaptability of both servers and clients. Let's break it down line by line.
Async with client.
This uses Python's Async context manager pattern. The async with block ensures the client connection is properly initialized and cleaned up, preventing resource leaks when the operation completes. FastMCP requires this pattern for all async client operations.
Templates equals await client list resource templates.
This fetches all available resource templates from the FastMCP server asynchronously. The await handles the non-blocking network call, returning a list of template objects that define available resources and their configurations.
Hash templates list MCP types, resource template. For template in templates.
This iterates through each resource template in the templates list, where templates contains all available resource template objects from the MCP server. The loop processes each template individually, enabling inspection and extraction of template-specific metadata like URIs, names, and tags. This is the standard pattern for batch processing collections of objects in Python.
Printf template URI, template URI template.
Outputs the template's URI pattern, which defines how resource paths are constructed for this specific template. This is critical for clients to know how to format requests when using this template, as the URI structure determines where and how resources will be accessed or created.
Printf name, template name.
This prints the human-readable name of each resource template, critical for users to identify templates when the URI alone isn't descriptive enough.
Printf description, Template description.
This prints the template's human-readable description, providing context about what the resource template does. Critical for users evaluating which template to use, as the description explains the template's purpose beyond just its name.
Hash access tags and other metadata. If hassetter, template, meta, and template meta.
This is defensive attribute access. Checks if meta exists and isn't empty before accessing it, preventing attribute error and handling missing metadata gracefully. Common pattern when working with optional or dynamic object attributes.
FastMCP equals template meta get FastMCP.
This safely extracts FastMCP specific metadata from the template's meta dictionary. The get FastMCP provides an empty dict fallback, preventing key error if the metadata key doesn't exist. This defensive pattern handles missing metadata gracefully while maintaining access to tags and other custom attributes.
Printf tags, FastMCP meta get tags.
This safely accesses the tags array from FastMCP's metadata, defaulting to an empty list if missing. The get pattern prevents key error crashes when metadata is incomplete, ensuring graceful handling of optional template attributes. Resource template discovery. The list resource templates pattern reveals how FastMCP2 treats templates as first-class resources, exposing their URIs, metadata, and tagging structure through a standardized protocol. Metadata access requires checking both the template object and its nested meta, FastMCP namespace, where tags and custom attributes live. This dual-layer approach keeps core MCP compatibility while enabling FastMCP-specific extensions.
The template that names every path becomes nameless in its own URI.